Assalamu alaikum students. Today's topic is going to be about Bernoulli's equation. Now, what is this equation about? Bernoulli's equation that relates the pressure, flow speed, which is the velocity, and height for fluid or flow of an ideal fluid such that mathematically which can be written as P1 plus half rho V1 square plus rho GH1 plus is equal to P2 plus half rho V2 square plus rho GH2. Now this can be simply written as P, which is the pressure, plus half rho, which is the density, and V squared, which is the velocity, plus rho GH, where G has the value of 9.8 meter per second square, and H is the height. Now this is equal to constant. So Bernoulli's equation is basically the relationship between all these quantities and they all relate to each other and they equal to a constant value. Now let us try to understand Bernoulli's equation with the help of an example. Let us consider a non-uniform pipe as you can see over here. The area of this pipe at the upper end, let's call the upper end 1 and let's call the lower end 2. The look at the upper end one, the area of cross section over here, which is A1, it is quite larger as compared to the area which is over here, A2. Now, in this case, we can see it that the area is very much different in both cases. And now, in this case, if we apply a force on one side of the pipe and the water flows from one side of the pipe to the other, let's say the force is applied over here, and in the lower case, that means at point 2, the force basically applies over here. Let's call that F2. And because of that reason, the basically fluid will flow through the pipe. Now, what will happen at this point? There will be pressure also on the liquid. That pressure, let's say at the top point, let's call it P1, and the pressure at point 2, let's call it P2. Now, in this case, we can see there's a difference as well of height. As you can see over here, the height is very much different. Let's call this H1 of the first end, and let's call this H2 of the second end. And what about the velocity? The velocity over here, the higher point is going to be lower, but as the fluid goes down the pipe, the velocity basically will increase. So the velocity in this case, let's call this velocity at point 2 V2, which is going out of the pipe, and the velocity which is going into the pipe, let's call that velocity V1. Now, in this case, as you can see, there's a displacement because of pressure and force. This displacement on the top level, let's call it delta x1. And at the bottom level, let's say the displacement was delta x2. And all of this was done in time t, delta t, that how much time it took from the liquid to move from one place to another. Now let us define and let us explain this what is happening with the help of mathematics. W where work is due to the force other than, let me rub it off so that it's clear. W is due to the force other than the conservative force of gravitation. So it equals to the change in the total mechanical energy, that is kinetic energy plus gravitational potential energy associated with the fluid elements. That means the work done will be equal to change in energies which is happening over here. We can write it down is like that W is equal to delta K, which is a kinetic energy, plus delta U, which is a potential energy. That means the work done by the liquid is equal to the change in energies in that pipe. Now this is from equation 1 and we are calling it equation 1. The total work done, as you can see, is the sum of the work done of the individual work done on pipe, let's say on the upper level 0.1 and on the lower level 0.2. So we can write down that mathematically that the total work W is equal to W1 plus W2. That is the net work done by the fluid inside the pipe. Now, how can we define work? Simply on the definition of work, we know that it is force into displacement. Now, in this case, we are only taking the work done on the upper level of the pipe, that is W1 on the upper pipe, and it is equal to force F1 into delta X1. And the force and displacement both are moving in the same direction, that is why W1 is equal to F1 into delta X1 cos theta. And as we know that the force and displacement are in the same direction, so theta will be equal to 0. When we put cos theta equal, or we'll put theta equal to 0 in cos theta, the answer will be equal to 1. Putting this value in this formula, what we get at the end, we get W1 is equal to F1 into delta X1. We are calling that equation number 3. Similarly, in the case of lower pipe, for the second end, we can say the work can be defined as W2 is equal to F2 into delta X2. But over here, the force and displacement are in opposite direction. The displacement basically is moving out of the uh, pipe. That is why there is negative sign. And we will prove it how it is negative sign. W2 is equal to F2 delta X2 cos theta. Here theta is equal to 180 because force basically is in opposite direction to that of the displacement. And cos 180, as we know, it is equal to -1. Putting this value in this equation, what do we get? We get therefore W2 is equal to minus F2 x2, and that is equation number 4. Now in this case we have found the work done on the upper pipe was F1 delta X1, which is equation 3, and the work done on the lower pipe, which is minus F2 delta X2. By the definition of pressure, we know that pressure is equal to force over area. So if we rearrange it, we can say that force is equal to pressure into area. So putting this value of force in equation number 3 and 4, because there is F1 and F2, instead of those, we are going to put them like this. From equation 5, equation 3 and equation 4 can be written as, for the upper end or the first end, W1 will be equal to, instead of F1, we are putting P1A1, and X delta X1 can be written as it is. We are calling it equation number 6. Similarly, in the case of the second end or the lower end, N2, W2, it will be minus because it is in opposition of force and displacement. Instead of force, we are putting down P2, A2, and the displacement part is delta X2. So now we have the force in equation 6 and equation 7. So this part is just related for force. First, we were discussing work. Now we are discussing force. Now, in this case, we know that since volume is equal to area into displacement. Let us consider this cube to understand it better. So this is a cube. How can we calculate its volume? The distance is, let's say, x. This is x and this is x. The height is x, the width is x, and the breadth is x as well. Now, first of all, we find out this area. Let's say this area x into x is a. And for the volume part, let's find out the volume. So we have to multiply by this x as well. So the volume will be equal to a into x, or we can say in our case a into delta x. And that is why we have written, since delta V is equal to A into delta X, which is equation number 8. By the definition of density, density is equal to mass per unit volume. So here it is, mass per unit volume. We rearrange it, we get delta V is equal to mass per unit density. Now this is a new equation. Now this is volume as well. Now we are comparing basically equation number 8 and equation number 9. By comparing equation 8 and equation 9, what do we get? Delta M over density is equal to area into displacement, which is equation number 10. Now, if we replace this area and displacement with mass per unit density in our equations, what do we get? Therefore, from equation 10, equation 6 and equation 7 can be written as the work done from point 1, it will be P1 into delta M1 divided by rho, which is equation number 11. And similarly for N2, W2 is equal to minus P2. Instead of A2 and delta X2, we are writing down delta M2 divided by density. And as we know, the density in this whole procedure will remain the same. That means the density of the material which is going into the pipe will be equal to density equal to which is getting out of the pipe. Basically, that is why the density has no numbers, because it is the same value. So we have equation 11 and as well as equation 12. Putting values from equation 11 and equation 12 in equation 2. Now we're putting these two values in equation 2, which is W1 plus W2. What do we get? The total work done, which is over here, is equal to P1 into delta M1 divided by rho minus P2 into delta M2 divided by rho. So this equation is the total work done by the upper pipe as well as the lower pipe. That means 1 and 2. Now, what about the energy part? For the energy, the change in kinetic energy can be given as delta K, which is equal to half M2 V2 square minus half M1 V1 square. Similarly, what about the potential energy? The net change in potential energy can be given as delta U, which is given by delta U is equal to delta M2 G H2 minus delta M1 GH1. Let us call this equation 14 and 50 respectively. Now, what about the total change in energy? Putting the values of equation 13 and 14 in equation 15 and equation 15, sorry, in equation 1. But what was that equation 1? The equation 1 said that W is equal to change in kinetic energy plus change in potential energy. So we're putting the values over here now. So what do we get? We get the change in total energy basically is on the right hand side right over here. As you can see that half delta M2 V2 square minus half delta M1 V1 square plus delta M2 GH2 minus delta M1 GH1. This is the change in kinetic energy plus change in potential energy. And what about over the left hand side? The left hand side is just because of work done, total work done. That means the work done on W1 minus the work done on W2. Actually, it was plus, but because the work done is over here in the opposite direction, that is why the negative sign multiplies and we have written negative over here. So here we are with our equation 16. Now what do we do? We are going to solve this equation so that it becomes easier. Let us rub this off so that it is clear to us. Now, since for an ideal solution, I may say the ideal equal mass should flow across both ends. Therefore, M1 is equal to M2. That means the mass which is flowing through the pipe is the same. So the mass is same in this case. That is why equation 17 has been taken over here. From equation 17, equation 16 can be written as P1 into delta M divided by rho minus P2 into delta M divided by rho. Now instead of M1 and M2, we have replaced it by delta M. And similarly over here on the right hand side, half delta M divided by V2 square minus half delta M V1 square plus delta M GH2 minus delta M GH1. Now all of these have M's in it. So let's just take common in this one. So delta M is taken common. So what do we get? We get delta M divided by rho. We've taken rho as common on the left hand side, but it is taken common from P1 minus P2 is equal to delta M is common from all of these values, which is 1 over 2 V2 square minus 1 over 2 V1 square plus GH2 minus GH1. Now we can cancel out these delta m because they are present on both sides. So what we are left with now, we are going to basically multiply density on both sides like over here as well as over here so that we can continue with our equation. So multiplying both sides with density, what do we get? We get rho will cancel out with this rho. It will be P1 minus P2 is equal to this rho will multiply with this whole term. So it will be 1 over 2 rho V2 square minus 1 over 2 rho V1 square plus rho GH2 minus rho GH1. Therefore, now we can rewrite it down. Now taking all the ones on one side, that means the upper pipe values on one side, that P1 half rho V1 square and minus rho GH1 on one side of the equation, let's say on the left hand side, and all the values of 2 on the other side. What do we get? P1 plus Half rho V1 square plus rho GH1 will be equal to P2 plus half rho V2 square plus rho GH2. Now this equation basically is representing the Bernoulli's equation. We can simply write it down as well as generally P plus 1 over 2 rho V2 square plus rho GH is equal to a constant value. So this is a Bernoulli's equation. Why? Because it is relating pressure, velocity, and height in the same equation. So the equation 18 and 19 are terms as Bernoulli's equation. Bernoulli's equation is based on the conservation of energy, such as for an incompressible and non-viscous fluid, that the total mechanical energy of the fluid is constant. I hope you enjoyed today's lecture. Inshallah, we'll meet again. Allah Hafiz. Bye bye.